Today we are going to be learning chapter 10, section 2, which talks about regression and finding the regression line. So, first of all, what is a regression line? A regression line is a best fitting straight line that allows us to make predictions about our data on a scatter plot. By creating a straight line with a given equation, we are able to normalize the data and make predictions about other possible data. For example, if we have data of the widths and weights of 20 polar bears and want to predict the weight of another polar bear that we know has a width of 40 inches but we do not want to or cannot weigh, we will be able to make an accurate prediction using the equation of a regression line, as long as the qualifications are met. We will talk on the next slide about what those qualifications are to use this formula. The regression line is also known as the least squares model. So here is a picture of a regression line. The red line is the regression line. It is going through the data points that we are given. As you can see, it kind of follows the mean and the trend. So we can use points along this line to make predictions about different X and Y values that we do not have. So what are the requirements for using this model and having it be accurate? So the first requirement is that the paired data from the sample is a random set of quantitative data. Second, that when the data from the sample is put on a scatter plot, the data appears to be roughly in a straight line. This shows that the data has a negative or positive trend that can be predicted by a straight line and not some other pattern. 3, remove any and all outliers that could be errors and consider effects of the outlier that strongly affects the data. Consider whether or not the outlier needs to be included in the data. So it's talking about outliers. We are going to go over outliers and influential points. An outlier is a point that is far away from the data. So here's an example of an outlier. Outliers can be influential or non-influential. So what an influential point can be an outlier or not, is a point that strongly affects the graph of the regression line. An influential point may be close to the data as well and not change it too much, but just enough, or it could be way over here as an outlier and it will really change the graph a lot more the farther away it is from the rest of the data. So you can see on this one, all these points are like exactly on this first line. We just got these 2 points over here that are shifting it upward and are going to change the trend. If we were to use this line and make predictions for 30, you would see with this line, it would be about 50. Here it'd be well over 60, probably about 70. So that changes about like 20 points, so that, you can see that makes a big difference. Sometimes the outliers are not influential, as you can see here. There's enough data to support this line that it's not going to shift it upwards through here, especially because this point is down here, kind of bringing the line back down again. So these outliers aren't affecting the data at all. Notation and formula. Okay, let's see. Do not know why this red box has appeared, but that is okay. So let's see. Sorry for the wait. Okay, so the equation for the formula of a slope is B1 equals coefficient R times S Y over S F. this is the standard deviation for the y values, this is the standard deviation for the x values, and is times by the coefficient for r. The formula for the equation of the y-intercept is b0 equals y bar minus 1, or b1x. So b1's the slope, and these are our two values. So the population, and then the notation here is kind of reviewer. Here is the equation of the regression line. So it was y equals b0 plus b1x, and that is for a population parameter. Of course, the lowercase b is going to be for a sample statistic, so you're going to have to determine beforehand whether you're doing this for a population or a sample. And so later, when you get this formula and you get the values for the slope and the y-intercept and the slope, you are going to be plugging in. Let's say you're giving a random x value, you're going to plug it in here, and you can get the y value. You can also plug in a y value here and get the x value by solving algebraically. Okay, next slide. So I have a TI-83 calculator. You can do, of course, I showed you some of these formulas, so you can do them by hand. I wouldn't recommend it though, because it is very time consuming and it's really easy to make a mistake. Plus, if you change in the data and for the questions or want to solve for the equation, it's going to be a lot easier if you just do in the calculator, so it has that information already, and you can review back to it as well. So the steps are as follows. First, go into your calculator, select stat, then edit, make sure you clear the list for L1 and L2. Enter the x variables in L1 and the y variables in L2. Then select stat, scroll on over on the top to tests, select line reg t-test, and then it's going to show you some information you need to fill out. So enter the list names L1 and L2 for the x and y variables respectively. So it's going to say L1 equals, put in the x values, L2 equals, it's going to give you x equals, and you're going to say L1, and y equals, you're going to say L2. So it knows where to pull that data from. Then you're going to enter 1 for frequency, and for B and P, select equals 0. This will test for a correlation versus no correlation, so you can tell if there's a correlation or not. Then select calculate and press enter. After you do that, it's going to show up like this on your calculator. So I wanted to include that so you know what you're looking at. So as in these steps, the A equals is going to be the slope. You're going to plug into your y equals ax plus b. And let's see, B is going to be the, I'm sorry, I think I messed that up. So A is going to be the y-intercept, and B is going to be the slope. So y equals y-intercept, x plus slope. After you do that, if given then after you find this, as I said before, you can plug in given x or y values to find predicted y or x values, depending on what information you're doing next using this line. It also gives you the R, coefficient R, and you can use this to see the correlation between the two values, and you can use this as well to determine if the regression line is a good model for the things that you're testing. Okay, so there are rounding rules as well when you're doing these calculations. When you find on the calculator, it's going to give you a lot of digits on there. It's going to give you something like this, like 3.8947. It might even go longer. So you're going to round it to make it easier, and generally the rules are to round B1 and B0 to 3 significant figures. So that just helps normalize the data, so when you're doing calculations, it's going to be accurate. You may be instructed to do so differently, and you can do as you're instructed to do 1 significant figure, 2, or 5, 10, whatever is going to work for your data, depending on how accurate you need or want to be. So an example of this rounding is if you get B1 equals 3.89478, you're going to round that to 3 significant figures at 3.895. You get the 5 because if you look at the third digit here, you go back to the one behind it. It is not equal to 5, but it is greater than 5. So you're going to round this up. So it's going to be 3.895. And as I mentioned before, you're also going to find the R value when you do those calculations. So what does the coefficient R tell you in this situation? So the R, it's going to tell you, so you can use it to see if there's a linear correlation. If you remember in the beginning, I said that there needs to be a linear correlation for you to be able to use this. So you can test for a linear correlation using R. So as stated in 10.2, if the R lies in the leftmost tail beyond the leftmost critical value, or in the right tail beyond the rightmost critical value, this is supposed to say right here, so that the absolute value is greater than or equal to the positive critical value, then determine that there's evidence to support there is in fact a linear correlation. If it is less than the positive critical value, then you're going to have to not use this formula. The mean of the Y values is going to give you the best prediction in that case, because you cannot use this model. The regression line that you're going to get is a straight line, and if it is not equal to or greater than, it means there's not a linear correlation. If there's a pattern that's going like this, a straight line is not going to give you accurate predictions, same as if it was going way above or way below or got wider at the end or beginning. There's some other trend going on, and you're going to need a different formula, or you're just going to have to estimate using the means to get the best prediction that you can. Make sure it's also not too far beyond the scope of the sample data. Like if your sample data is way down here in the line, maybe it kind of falls, but it's like way up there, it's probably not going to be a good prediction as well, because there's probably an outlier or something influencing it, and everything's going to be seen way higher or way lower than it actually is. Okay, in this chapter, you're going to come across marginal change. What is marginal change? It is the amount that one variable changes when another changes by exactly 1 unit. For example, the slope in the regression equation shows the marginal change if x changes by 1 unit. This will affect the y value, and through the marginal change, we will be able to see by how much. So as an example here, let's say we have a regression equation, and it shows us the amount of products need to be sold each year. And how much we need to sell each year here is based on demand from last year. And the demand from last year goes up by 1 unit. In this case, representing 1,000. So we're going by thousands here because we're selling a decent amount of products. So 1 unit is 1,000. So the slope will give us the marginal change and will give us how many additional products that we need to make each year. So if this is our regression equation, we have y hat equals negative 3.21 plus 3.0 times x. If we change x by 1 unit, we're going to multiply it by the slope, 3, and we're going to get 3 times more product. We also learned about the residual in this chapter. The residual is a comparison between the predicted value of y and the actual measured value of y. So if you get the regression equation and you're going to see the line that's going to show the predicted, The actual plots are the actual ones. And if we were to predict something and then actually measure it later, that's going to give us the actual. So we can compare it. So it's going to be the actual minus the predicted. To determine the accuracy of your regression line, you can use a residual plot. A residual plot is a scatter plot that shows these residuals. So every x values are going to stay the same, but the y values are going to be replaced with the residual. So the graph will show x, comma, y minus y hat. The residual plot will appear in a straight horizontal line that will go through the scatter points and be closer to the points. And the closer it is to the points, the closer the predictions are. Check for any patterns that suggest, again, that this is not a good model for representing. Also, if it becomes wider towards the end or beginning. That's another clue that this is not a good formula for your data set. The least squares property. This ties into it being called the least squares line. The least squares property is satisfied when the line shows the sum of a line that has the lowest sum possible when you square all the residuals and add up the sum. So if you go back to what we were talking about before about the residuals, the actual minus predicted, if you square each of those values, so the y minus y hat, I had to draw these y hats on, so that's supposed to go over here, and then you square that and you add them all up, the lowest possible line that can give us the lowest sum is going to be the least squares line. Our calculators fortunately do this for us, so we do not have to worry about it, but it is good to know that the lines that we get are going to give us the lowest possible value for this, and they're based upon this. These are my credits. This is me, Riley Adams. Thank you guys for listening today. This project was courtesy of Math M15 project, where we each taught a lesson that we learned this semester. Thank you guys so much, and good luck on the final.